Another property of action potentials is their ability to spread like a wave down the membrane. And propagation is the term that we use for the spread of the action potential down the membrane of the neuron axon. So propagation does not involve a single action potential moving down the membrane. Rather, an action potential that's created in a small part of the membrane is the stimulus that will create a brand new action potential in an adjacent region. So it works a bit like a domino effect, where a domino falling over is the stimulus that's going to topple a nearby domino. So in this diagram, it is showing a sequence in which we have three action potentials that are created in a small region of the membrane. In the top part of the diagram, there's an action potential that is beginning on the left side of the membrane. And in the center, we see that a new action potential has begun in an adjacent region. And the bottom diagram is showing the exact same thing, with a new action potential being created as a result of an action potential occurring in an adjacent region to the left. So recall that action potentials begin with sodium entering the cell through the plasma membrane and ending when potassium leaves the cell through the plasma membrane. Sodium entering the cell at the start of the action potential is referred to as the depolarization phase, while potassium exiting the cell is called the repolarization phase of the action potential. The depolarization phase of the action potential is what triggers the start of a new action potential in an adjacent region or an adjacent segment of the membrane. So action potentials will always spread or propagate away from the neuron soma. They begin at the axon hillock and propagate or spread down the axon towards the axon terminals. So now that we've seen how action potentials propagate down the axon, let's see how those action potentials cause the release of neurotransmitter into the synaptic cleft. So we've seen this process occur at the neuromuscular junction when we saw how muscles contract, and the events that occur here are exactly the same. So let's do a quick review of it, but then also elaborate on some additional points. So an action potential that was created in the neuron will propagate down the axon of the neuron and will arrive at the axon terminal, which, as you recall, the axon terminal is the expanded end of the axon that stores neurotransmitters. So that's what we're seeing at step 1 here. When it arrives at the axon terminal, the voltage change of the action potential, because recall that the action potential is really just a brief voltage change across the membrane. The action potential causes the structures that are in the axon terminal called voltage-gated calcium channels to open. And this is going to allow calcium to enter the axon terminal of the presynaptic neuron. So calcium will then enter the axon terminal, and that causes the vesicles that are storing the neurotransmitter to fuse with the plasma membrane. And in doing so, they're going to empty the neurotransmitter that they're carrying out into the synaptic cleft. That neurotransmitter will then diffuse across the synaptic cleft, because that's a very short distance to diffuse. So it diffuses very quickly and very easily. And upon diffusing, it will bind to receptors that are very specific for that neurotransmitter. These receptors may be located on the dendrites or even on the soma of the receiving neuron, that is the postsynaptic neuron. That receptor will then become activated as a result of the neurotransmitter binding to it. The receiving neuron, which is the postsynaptic neuron, will then go on to create its own action potentials in response to the activation of the receptors. So if enough receptors are activated, then the receiving cell will likely fire an action potential as a result. However, if only a few receptors are activated, that may not be a strong enough stimulus to reach that critical threshold point for generating action potentials. So now that the postsynaptic neuron has been signaled, any excess neurotransmitter that's remaining in the synaptic cleft is very quickly removed in one of two ways. And the reason that it's removed is so that it prevents overstimulation of the postsynaptic neuron. So one of the ways that it's removed is that it's removed by enzyme breakdown. That is, there are specific enzymes on the postsynaptic membrane that will destroy that neurotransmitter. The neurotransmitter may also be removed by a process that's called reuptake. And that's a process where the presynaptic neuron will essentially reclaim any unused neurotransmitter. And what it will do is it will repackage it into new synaptic vesicles and store it in its axon terminal until it can be used or released later.